This is our first example from our retaining wall problems. We're going to determine the resultant force and location on the wall at the at-rest condition. So that's our K naught condition. And the first thing we're going to do is use our, add some information. We're missing OCR equals 1.5. And we're going to use our K naught correlation, which is 1 minus sine V prime, which is the friction angle, times OCR, which is the over-consolidation ratio, and that's raised to the sine of phi prime. So when we plug in what we have 1 minus sine of 35, 1.5 raised to the sine of 35, and that equals 0.538. Now, what we're going to do is determine the pressure distribution behind the wall, and then find the location and the magnitude of the resultant force. So at Z equals 0, that's point A, our vertical effective stress equals 0, our pore pressure equals 0, and therefore our horizontal stress, which is K naught times sigma prime V, is also 0. At Z equals 3 meters, which is point B, our vertical stress is 3 times 15.7, which gives us 47.1 kPa. And our pore pressure is still 0 because we're at the groundwater surface here, groundwater table. And our horizontal stress then becomes K naught sigma prime V, which equals 0.538 times the stress we just calculated, 47.1. And that answer is 25.34 kPa. So then the final point we need to calculate is what happens at the bottom of the wall. So that's when Z equals 4.5 meters. So that's point C. So the stress then is 3 times 15.7 plus 1.5 times 19.2 minus the pore pressure, which is 1.5 times 9.81. So that equals 61.19 kPa. And the pore pressure we just calculated as 1.5 times 9.81, and that equals 39.92 kPa. The horizontal stress then becomes 0.538 times our effective stress, 61.19. That equals, oh, I'm sorry, this is not 39.2, this is 14.72, and this is 39.92. So now that we have each of the horizontal stress and pore pressure for along our wall, we can plot them. So this is the horizontal stress with depth. This is the pore pressure with depth. So we just said that it'll be a straight line to here, and at 3 meters, this becomes 25.34, and then it increases to, at the base of the wall, point C, to 39.92. The pore pressure is 0 until we get to 3, and then it increases to 14.72. So both of these distributions are going to act together to get our final distribution of horizontal plus pore pressure. So that'll be 25.34, and this becomes 54.64. So now that we have the distributions behind the wall from the soil and the water, we can find the resultant force by finding the areas. So if you see that this can be subdivided into a triangle, a rectangle, another triangle, and this is another triangle. So you can either find these four areas or you could break it up and find the area here. So in this case, I did these four areas. So for the P1, which is the pressure, the resultant pressure in the first triangle, that's 1/2 times 3, which is the height of the triangle, times the base of the triangle. And that answer is 38.01. For the second one, it's a rectangle. So now we just need the width times the height. And we still get 38.01. For the third triangle, it's the 1/2 the height times the base, which in this case is 14.58, which is the difference between this and 25.34. That is 10.94. And then the fourth is a triangle, 1/2 times 1.5 times 14.72. And that gives us 11.04. So now if we just sum up all our pressures, we can get our resultant pressure. And so when we add all those up, we get a pressure of 98 kilonewtons per meter of wall. That's our first answer. Now we need to find the location from the bottom. So we're going to call that Z bar. It's the location of P from bottom of wall. And to do that, we're going to multiply each of the pressures by their location from the bottom. So P1C plus P2 times P2C plus P3 P3C plus P4 P4C. And divide that by the resultant. So when we do that, we get 38.01 times 1.5 plus, so each of these resultants each of these forces act in a different location based on the geometry. So for example, for the triangle, it's going to act 1/3 from the base. So in this case, 3/3. For the rectangle, it's going to act halfway. So in this case, 1.5 divided by 3. The other triangle that's here also acts at 1/3, which in this case is 1.5 divided by 3. And the last triangle from the water also acts at 1/3, which is 1.5 divided by 3. So for this first one, P1, it's acting at 1.5, that's this height, plus the height of the triangle, which is 3/1/3 up. So this is 3/3. The second force, P2, was 38.01, and it acts at 1.5 divided by 2. The third force was 10.94. It acts at 1.5 divided by 3. And the fourth force is 11.04. And it acts at 1.5 divided by 3. And then we divide all of that by 98. And so we calculate the location as 1.76 meters from bottom.